In this next video, we're going to talk about heat and do a specific calorimeter problem. Okay. And a calorimeter problem is used to find the amount of heat absorbed in a reaction or phase change. That would be an endothermic reaction, or the amount of heat released. That would be an exothermic reaction. Heat is an extensive property. In other words, it matters how much we have. So mass does matter, and the unit of measurement that we use is joules. We can convert joules to calories, but we will not go into that just yet. The formula that we use is Q equal MC delta T. And what do all those variables mean? Well, Q is heat. That is what we're solving for. The unit of measurement is joules. M is mass in grams. Delta, when I say delta, I am talking about this specific symbol right there. Delta T is the change in temperature, and CP is specific heat, or the amount of heat to raise 1 gram 1 degree Celsius. Right? That is the definition of specific heat. It is the amount of heat in joules needed to raise the temperature of 1 gram of a specific substance 1 degree Celsius. And we use specific substance because specific heat will change depending on what you are looking at. The specific heat for water is not the same for aluminum. They are completely different. Different elements and compounds have different properties in terms of holding or releasing heat. We use specific heat if the temperature is being changed. We're not going to use this variable if we are changing phases. So what do we use if we change phases? Well, if we are looking at the amount of heat absorbed when a substance is melting from a solid to a liquid, or the amount of heat released when a liquid is freezing into a solid, we will use heat of fusion. If we want to know the amount of heat absorbed when a substance is evaporating from a liquid to a gas, or the amount of heat released when a gas is condensing into a liquid, we will use the heat of vaporization. Heat of vaporization is the phase change at the boiling point. Heat of fusion is the phase change at the freezing point. So let's take a look at a specific problem. Here is the heating and cooling curve for water. There's our freezing point at 0 degrees, and there is our boiling point at 100 degrees. And we want to know what is the heat absorbed when 5 grams, so that's how much we have, of water is heated from -5 degrees to 120 degrees. So we're starting down here, and we're going all the way to up here. Okay, so we're going through several different regions on our heating and cooling curve. This is not going to be one calculation. So what values do we use at what points? Well, temperature is changing here, here, and here. So we're going to use specific heat when we are calculating for the heat in those regions. At these plateaus, phase changes are occurring. So at B, that's our freezing point, we're going to use the heat of fusion, and at D, we are going to use the heat of vaporization. All right, so let's set up our problems, set up our equations, and then plug in the numbers. In region A, when we are going from -5 to 0 degrees, we are going to use the formula Q equals mass times specific heat times change in temperature. Then we need to know how much heat is necessary to melt that amount of ice. For that, Q is going to equal, the heat is going to equal the mass of the ice times the heat of fusion. Once we have melted it into a liquid, we need to raise the temperature 100 degrees. And to find out how much heat is necessary to do that, we're going to multiply the mass times the specific heat of water times that change in temperature. Now that we have all of the water at 100 degrees or its boiling point, we need to know how much heat is needed to change the phase from a liquid to a gas. To do that, we're going to multiply the mass times the heat of vaporization. And finally, how much heat is it going to take to raise the temperature from 100 degrees to 120 degrees. To do that, we are going to multiply mass times the specific heat times the change in temperature. Okay. To do these problems, we do need to have the values for the substance that we're looking at. And for water, specific heat is 4.18 joules per gram degree Celsius. See that degree Celsius, what temperature is changing. Heat of fusion is 334, and heat of vaporization is 2,260 joules per gram. All right, for A, from this region, this section here, we need to plug in the numbers. Q is going to equal 5 grams times 4.18 joules per gram degrees Celsius times 5 degrees Celsius. We're going from -5 degrees to this point here, 0 degrees. And that will take 104.5 joules. Now we need to find out how much heat is needed to completely melt that ice into a liquid. That's region B. So let's plug in the numbers for that. Heat is going to be equal to the mass, 5 grams, times the heat of fusion, which is 334 joules per gram, for a total of 1,670 joules. Now that we've melted it all into a liquid, we need to figure out how much heat is needed to raise the temperature to 100 degrees, or the boiling point. For that, we're going to solve heat by multiplying the mass of the substance, 5 grams, changing temperature, so we're going to use specific heat, 4.18 joules per gram per degree Celsius, times 100 degrees, because we're going from 0 to 100 degrees, so the change in temperature is 100 degrees. That would be 2,090 joules. Now we have to find out how much heat is needed to evaporate off that liquid. We're going to multiply, mass hasn't changed, 5 grams, times, this time we're going to multiply it by the heat of vaporization, or 2,260 joules per gram. That will give us 11,300 joules. Notice the difference between the heat needed to evaporate and the heat needed to fuse. Quite a big difference. And finally, we need to raise the temperature of that gas to 120 degrees. So we're going to multiply the mass. Whoops, sorry about that. We're going to multiply the mass times the specific heat times the change in temperature, which is 20 degrees. So now we have values for all of these regions. The last thing that we need to do is we need to add all of those values together. And when we do that, we get 15,582 joules, or if we convert it, 15.5825 kilojoules. This is a pretty long, extensive problem, but hopefully you get an idea of when you use heat of fusion, when you use specific heat, and when you use heat of vaporization.